In the previous example, we saw how we can solve a quadratic equation using the quadratic formula. And the example that we looked at was an equation that was already written in standard form. By standard form, we said that the equation was written such that all the terms were on one side of the equation, written in descending order, and the other side is set equal to 0. And once that term is in standard form, we were able to identify certain values of the quadratic formula that we need to plug in, namely the A, B, and C values. We said that as long as we know the B value, the A value, and the C value to plug into this formula, we can ascertain our solutions to solve the equation. And we looked at equation 7x squared plus 7x plus 10, which was already written in the standard form, and from that equation we were able to extract our A, B, and C values. We're going to look at an equation that's not quite in standard form, and we're going to consider some things that we have to do to write the equation in standard form. Once again, if you're using the quadratic formula, the equation must be written in standard form, and that form requests that the equations be written in descending order and the other side be set equals to 0. So with this particular equation, one of the things that we need to do to rewrite this equation or transform it to this form, to standard form, is we need to try to get all the terms that are like terms combined and the other side set equals to 0. In order for us to do that, we have to go ahead and try to FOIL this guy out. And as long as we FOIL this guy out, we'll be able to identify our like terms. So first thing I'm going to do is I'm going to rewrite this binomial square as the product of two binomials. So I'm going to rewrite this as, sorry about that, I'm going to rewrite it as x minus 5 squared. I'm going to rewrite it as x minus 5 times x minus 5. So x minus 5 times x minus 5 is equals to 2x. And once I have it written as the product of two binomials, which is what this is implying, saying this guy, quantity here, can be expanded by writing it out twice. And now I'm going to use the process of foiling. So FOIL is first, outer, inner, last. So first means I multiply the two first terms of the binomial. X times x gives me a result of x squared. Outer means I multiply the two outer terms. X times a negative 5 gives me a negative 5x. So that was our first. This is our outer. And our inner means I multiply the two inner terms. Negative 5 times x. Again, that gives me a negative 5x. And the last terms in each binomial, I multiply the negative 5 times the negative 5. And again, I'm taking into consideration the signs. Negative times negative is positive. 5 times 5 is 25. So this becomes plus 25, and then this guy is still over here on the other side of the equation. First thing I want to do is I want to combine my like terms. These two terms are like terms of that equation, so I want to combine those terms. Negative 5 minus 5x, minus 5x, minus 5x, they're like terms because they have the same power on the same variables. So we combine them by saying negative 5, that's negative 10x. We're not multiplying, we're just combining or adding or summing like terms. Negative 10x plus 25 is equals to 2x. And now we notice that at this point, at this step, we have like terms that are on opposite sides of the equation. And to combine like terms on opposite side of the equation, we said that we need to use our properties of addition or subtraction property of equality. In this case, we're going to use the subtraction property of equality, which means I'm trying to get this guy over here. So I need to subtract 2x from both sides of the equation in order to be able to get it on the other side and combine it with the like terms. that's on the other side. So I'm going to subtract 2x from both sides, or I can just simply move it over and change the sign of it. So this becomes x squared minus 10x, and then a minus 2x because I'm subtracting 2x from both sides essentially. So minus 2x plus 25, and then 2x minus 2x, that gives a result of 0. So we're almost there as far as the request that our quadratic formula is making on us in order for us to be able to get our a, b, and c values. So this is minus 10x minus 2x. This becomes a result of negative 12x plus 25 is equals to 0, and this is x squared. So at this point here, the equation is written in standard form, and we know that it's written in standard form because all the terms are on one side of the equation, and the equation is in descending order, which means according to the degrees, 2, 1, and constant, the equation is written in descending order. So once the equation is written in descending order, all the terms are on one side, the other side set equals to 0, which is the request in order for us to be able to use a quadratic formula. That's the request that is made upon the equation in order to use a quadratic formula. Once we have that condition met, we can now identify our a, b, and c values, and the a value is just simply the coefficient of the squared term or the quadratic term. So a in this particular case is equals to 1. If you do not see a value here, it's understood to be 1. B is a negative 12, so b is equals to negative 12. We also consider that sign as well, and c is equals to 25. So now, once we have our a, b, and c values, we're at the point where we can go ahead and plug into our quadratic formula. The formula, we look up here again, it's minus whatever a b is. Now this negative or this minus sign is a part of the formula, and you do not want to consider the sign of the b value to be substituting that minus sign. It's incorrect. You have to always write that sign out. So it's minus whatever the b value is, and to avoid the tendency to doing that, you want to just, whenever you make a substitution, use parentheses. So minus the b value of this equation is a negative 12, plus or minus the square root of that negative 12 squared, minus 4 times a is considered to be 1, and c is 25. And that's all over 2 times a, which is 1. This point, now we're going to simplify this whole situation that's underneath the radical. So we have x is equals to, well, whenever we have here, we have here a double negatives. Whenever we have a double negative, that becomes positive, because essentially you can say you're multiplying a negative 1 times a negative 12, which negative times negative is positive, 1 times 12 is 12. So that's 12 plus or minus the square root of negative 12 squared is 144. 144. And then this becomes 4 times 1 is 4. 4 times 25, that's 100. There's a minus sign here, so it's minus 100. All over 2 times 1 is 2. At this point, now we're going to simplify that a little bit further. So let's go ahead and use up here to simplify it further. So we have 12 plus or minus the square root, well, 144 minus 100, that gives a result of 44 all over 2. So now when we get to this point here, if you notice, 44, because we want to simplify this situation that's underneath the radical, and in most cases when you use this particular formula, the value that's underneath the radical is usually a perfect square, but there are cases where it may not be a perfect square. Well, the way you handle that is you have to try to rewrite this as a product of its factors, such that one of the factors is the perfect square and the highest perfect square in that factorization. So what I mean by that is 12 plus or minus the square root. Well, instead of 44, I want to rewrite 44 I want to rewrite it as a product of two factors. And I want to look for some factors such that one of the factors is a perfect square. So when I'm thinking about rewriting it, I'm starting with 1 in the number itself, 1 in 44. Well, you're not really going to ever use the 1 in the number itself, but let's go on to 2. 2 and what gives me 44? Well, 2 and 22, are any of those perfect squares? None of those are perfect squares. So we can go on to the next number. 3 does not go into 44 evenly, so I'm going to skip that. How about 4? 4 and what gives me 44? 4 and we know 4 times 10 is 40. 4 and 11 is 44. Well, 4 and 11 is 44. Well, 4 is the perfect square. It's the highest perfect square in the number. I know that because whenever the other factor is a prime number, then that essentially means I've found the highest perfect square in that particular factorization. So I can rewrite 44 as the product of 4 times 11 all over 2. And then I can go ahead and simplify this further by saying this is 12 plus or minus the square root. I can use a property that's called the radical property, which means if I have the square root of 2 factors underneath a radical, I can rewrite it where I put each factor underneath a separate radical. So I can rewrite this as the square root of 4 times the square root of 11 all over 2. And by doing that, I'm doing that so that I can simplify the perfect square. So this becomes 12 plus or minus square root of 4 is 2. This cannot be simplified because it is a prime number underneath there. So I just write it as it is, square root 11 all over 2. Now with this step, you can go ahead and break this up, or you can look and say I have a common factor in all 3 terms, so I can cancel out that common factor. And the common factor is 2. 2 goes into 12 6 times, 2 goes into 2 1 times, 2 goes into 2 1 times here. Now the only time you can do any sort of canceling at this step is if you can cancel in all 3 places. If you cannot cancel in all 3 places, do not cancel at that particular step. So we can go ahead and cancel or break it up at this particular step to say that, well, one of our solution is 12, then the plus version of this situation plus the 2 square root 11 all over 2, and then the other situation is 12 minus 2 square root 11 all over 2. So we can now go ahead and show the cancellation. 2 goes into itself once, 2 goes into 12 6 times, 2 goes into itself once. So the result that remains here is 6 plus 1 square root of 11, or just the square root of 11. That's one of our solutions, the same thing here. So that becomes 6 minus 1 square root of 11, or just, we can just rewrite this as 6 plus the square root of 11, 6 minus the square root of 11. And these are our 2 solutions here. And again, we can go ahead and check the solution back into our original equation, and you will see that it will satisfy the equation. So let's go ahead and look at the steps again to use the quadratic formula. Once again, first step is we ensure that the equation is written in standard form and in descending order. If the equation is not in standard form, use algebraic properties such as what we did all over here to transform the equation to standard form. Once the equation is in standard form, identify the values for A, B, and C and pay attention to their signs. The third step is we plug in the A, B, and C values into the formula and solve and simplify. And then the last step is we go ahead and check our solutions back into the original equation. And if the solutions satisfy the original equation, then we say that the solution is a valid solution and we keep it as our solution to the equation.